Okay, so I'm Victoriya Kalmanovich. I'm a software group lead in the Israeli Navy. And today I'm not going to talk about the Python library that's going to change your lives. And I'm not going to talk about the machine learning algorithm that's going to turn you all super rich as soon as you walk out the door. But I am going to talk about data science, and I am going to talk about things that, for me, they're a little bit different and out of my comfort zone, like engines and machines. And I hope that by the end of my talk, you will all think it's super cool and that this concept is going to walk with you as soon as you leave this door. So I started out as a software engineer in the Army, and I'm a computer engineer, and I've done some really cool projects on defense systems and on autonomous vehicles navigation. And then in my final role, I'm a software group lead to 3 teams who do really, really cool things. And my story actually begins about 3 years ago when one of my project managers came into the room, and we were sitting in the morning and having a cup of coffee together. And he started ranting about the last time he sailed. Now, I don't know how many of you actually know maritime organizations or navies, but people in the Navy, at least in Israel, they have their day jobs. But if they've done courses where they know how to sail a certain type of vessel, they have to leave every once in a while and go sail in order to do some training. And he was one of those guys who had to go train every once in a while, and he was sailing a lot. And he told me that when he was sitting in the vessel, he couldn't perform his job in the vessel because he kept listening to an engine at the back of his head that was making a really specific sound. Now, this guy sails a lot, and he knows exactly what the sound means. And I was trying to be a nice friend, and I said, oh, I wish there was an app that could do that instead of you. And we laughed for a moment, and then we thought about it a little bit more, and we said, why wouldn't we do an app that could classify those sounds instead of you? And that's where the project began. Now, when it comes to software projects, we pretty much know what we're looking for. We know the documents we're looking for. We know the milestones. We have a certain vision of what we're trying to get to in the end. But this was no regular software project, because this project had things like maintenance and engines and a lot of things that I had nothing to do with. And at first, I felt like I didn't know where to even begin. But then I decided to start with the problem I was trying to solve. And the problem I was trying to solve was to try and predict faults in engines, which is called maintenance. Now, we probably know maintenance from our cars. There are 2 types of maintenance in companies that have big machines, like ships or like airplanes or like trains. And I know that I have to take my car every 20,000 kilometers to the shop. And I know that they go over the brakes and they go over whatever it is they have to go over, a set of rules, in order to prevent any type of fault that may occur. But we also know that faults occur. And that's where the other type of maintenance comes in handy. It's the breakdown maintenance. Breakdown maintenance means we did everything we could, but we couldn't prevent the fault. And now we have to fix it. We have to find a fix for after it happened. So when it comes to cars, it's a little bit uncomfortable, and you have to take the bus for a few days. But when it comes to ships, it's a little bit more than that, because a ship has missions it has to perform. And when a ship is down, it's broken, it can't perform its missions, and then other ships will have to perform its missions for it. And you have to buy spare parts. And if there are spare parts within the country, then you're in good shape. But if there are spare parts in another country, then you have to wait for them to arrive, and then you have to wait for them to wait at customs. And when they finally reach their destinations, you have to take all the technicians who need to fix that fault and shift them from their regular jobs in order to fix this ship. So it's one big mess. So preventive maintenance doesn't fix all types of faults. It doesn't prevent all types of faults. And breakdown maintenance is just the worst case scenario. So that's when the world decided to go into a new field called predictive maintenance. And they started researching this field because it seems like just the in-between of the preventive and the breakdown, right? So like many amazing things that have happened in the past, the field of predictive maintenance also began at NASA in the beginning of the 90s. A bunch of mechanical engineers were sitting around a table yelling that they're not doing maintenance good enough. And one of the engineers said, I want to do an experiment. I want to collect some data. And he did. He took 100 space shuttle engines, and he collected some data. He didn't really know what he was doing. It was really the beginning of predictive maintenance. And what he found out was that out of the 100 space shuttle engines that he tested, only 4 actually needed attending to. And the other 96 didn't really need preventive maintenance or didn't even need any treatment at all. And that's when NASA decided to pursue this field of predictive maintenance, because what a waste, right? And so how did NASA do it? NASA did it using physical models. It means you need to know exactly how the engine behaves at all times. You need to know how the engine changes its behavior. You need to know how the environment affects the engine's behavior. You need to know everything there is to know. You need to be a mechanical engineer. And basically, the mechanical engineer, that's what they used to do in companies that do predictive maintenance based on physical models. They look at the engines. They write the set of rules that they know based on the engine's behavior. And they let the rules tell them the outcome. But there isn't just one way to collect data or to do physical models. There are many ways. You can do vibration analysis, which means you collect data based on how the engine vibrates. You can do oil analysis, which means you take the engine and after the sale, or if we're talking about ships, and you check how contaminated the oil is after it sails. And you can do acoustic analysis based on vibrations. And you can do many, many, many things in order to just get to the point where you have to write a set of rules based on physical models. So at the beginning, I thought I was going to do this project based on a physical model. And I would find a mechanical engineer somewhere that could help me. And I started looking at the most common way to do physical models, which is based on vibration analysis. Vibration analysis means we take our vessel and we put a lot of equipment throughout the vessel, and then we test how the engine vibrates. And then I thought, OK, so I need a computer engineer to help me set all the equipment. I need a computer engineer to help me collect the data. I need a computer engineer to write the set of rules, the physical models for me. And I need a mechanical engineer to help me understand the outcome, and if there is a fault, also to fix the fault. So I need a mechanical engineer all the way with me. And not every mechanical engineer is a vibration analyst, so I found out. There isn't just a tutorial on YouTube saying, hey guys, today I'm going to teach you how to become a vibration analyst, unfortunately. And then I said, OK, since I don't have a mechanical engineer just lying around waiting for me just unemployed, waiting for work, let's see if maybe NASA did something that's a little better. So NASA really did something a little bit better, because NASA automated some parts of the process. They automated the way they collect the data, and they automated the way that they process the data. But they still had a mechanical engineer in the loop throughout the entire process. And at this point, I said, OK, so it's either I find a mechanical engineer and I hand this project over, or I'm going to have to just follow him around and ask him, what's next, what's next, what's next? And I really didn't know at this point what to do. I thought maybe I'll just drop it. But then I remembered that there's this amazing thing called data science. And I thought, OK, this is engines, this is maintenance. But still, I can do something with things I know from data science, right? I'm not a computer engineer for nothing. And that's where I decided to look into how I'm going to do this project using data science. Now, data science models, what they say, actually, they do the same thing like the physical models. You still have to collect all the data, and you still have to understand the data using a mechanical engineer who can help you with understanding and creating all your tables and your data sets. But as of this moment on, you don't tell the rules. You ask the data to tell the rules instead of the person. And I felt uncomfortable going into a project where the whole world is doing it based on physical models, and mechanical engineers are actually ruling this field. But because I saw that a lot of projects are moving forward with data science, and because I saw that there are a lot of insights that currently mechanical engineers are missing out because they're not going into data science, I decided to pursue. And so just like we collect data from machines in many ways, we can start shifting our mind and thinking about how we collect the data for the data sets that we're going to create. So we can either collect data from the sound of that the machine makes, or we can collect data based on the way that the engine looks, or the way that the engine rusts, or any other way. And the data collection has to be very, very accurate. So does anybody know that it's not the same person? Okay, perfect. And this is exactly what I mean when the data collection has to be accurate. Because if we collect data that is not accurate, then we can make mistakes eventually by letting the data give us the rules. So the data collection has to be really, really accurate. And when I'm thinking about really the difference between physical models and machine learning models, then I'm just really it's the most simple way to explain it to myself. If I take, for example, your face, and I try to distinguish between the two, it's going to be relatively easy, right? Because I'm going to write a set of rules, and it's going to be fine. Eventually, I will make it. But once I take all your faces and I try to distinguish between all of them, it's going to be a little bit more difficult and maybe even impossible for me. And the same thing goes for engines, because each engine sounds a little bit different or seems a little bit different. And that's why I need the data science in order to help me where I can't translate things from my mind into the page. So I decided to go and look only in two directions, unsupervised and supervised. I didn't go to reinforcement at that point, so we won't talk about reinforcement today. So I said, OK, let's say I collect data. Let's say I collect data, sound data. And I don't know the sound data. I don't have time to tag it. I don't have the manpower to tag it. And I'm just going to take all this data. I don't care what this data is. And I'm going to ask the supervised algorithms to cluster it for me. I don't care that it's bananas or whether it's apples or whatever it is that my data is. I just want the algorithm to help me cluster the data. So for example, if I have a lot of sounds from a lot of engines, this clustering algorithms can help me say which engine makes each sound. And the other thing that unsupervised algorithms give us is once we have the information for each engine separately, we can do anomaly detection on each and every one of them and try to see where the behavior changes a little bit. So that's what I thought I was going to do. And then I remembered that I don't have a good enough data set. And then I decided to go look into supervised, because I said, OK, I can maybe buy a data set online, or maybe I can find somebody who's already collected a data set. Because it's really important for me to try and just understand and just get a feel of how engines behave and if this project is viable. So I went in and started looking into supervised. And what supervised means is we give the machine, for example, a photo of a dog, and we say it's a dog. And then we give another photo of a dog and say it's a dog. And then when the algorithm gets a photo of a dog that it doesn't know, then it knows it's a dog. It can say it's a dog. And supervised algorithms, they also have to be trained very well in order to make the distinctions between in the subcategories. For example, we can say it's a bird and a bird and a bird, but a really good algorithm will also be able to say which type of bird it is. So if I'm looking at engines, it could tell me that the engine is broken or it's working, but if my algorithm is trained well enough, then it can tell me exactly where in the engine the fault is going to occur. And so before we're going into predictive maintenance projects, we need to keep in mind a few simple things that distinguish this project from many of the data science projects we see out there. So the first thing is how we collect the data. I can't just go scrape the web for data from actual engines. So I have to have sensors all over the vessel I'm trying to collect data from. And the more sensors I put, the more accurate my data is going to be. My data collection is going to be. For example, NASA, they had 21 sensors on each and every one of the engines. But not all organizations are as rich as NASA. And also, there are a lot of other issues with sensors. For example, Bluetooth and Wi-Fi technologies are not allowed on all types of vessels. And sensors is like a whole thing. But it's really important to keep in mind that I can't just go and get data from other places, and I have to start collecting right now from an actual engine. And the other thing that's important, as I said, I didn't have a data set, but I found a data set online. NASA were generous enough to give a free public data set of, I think, 30 years of machine information. And that really helps you, in case you want to go into predictive maintenance projects, that really helps you understand how you want to create this data set, where you want to start, and how you want to start. So creating a big enough data set and that can give you actual insights is really important also. And the third thing is what we're trying to find. Okay, we collected the data. We know how the data looks. What are we trying to find? So I was trying to find a time. I was trying to find this machine is going to break in 3 hours. This machine is going to break in 10 hours. So my data has to be time series data because I'm trying to find a time. And after I've established all the prior conditions, I could go into the actual data science. Now, the way it is done in many of the projects out there that are shifting themselves into data science in the field of predictive maintenance, they do it based on something called RUL prediction, which is the remaining useful lifetime of the machine. So the first thing you really need to do is choose a model. Sounds easy, right? Choosing a model is not easy at all. You have to know the problem really, really well. A lot of people, they start projects by choosing models they think can get them to a certain point, but their actual problem they're trying to solve is very, very poorly defined. So in this case, I could choose between two types of models, between classification and regression. And in order to understand each way I'm trying to go, I had to understand exactly what I'm trying to find. So for example, if we have a neighborhood of houses, and each house was sold at a certain price, and I'm trying to understand which price the last house in the neighborhood is going to be sold at, I can do it in two ways. I can either say, okay, choose from the categories of the already sold prices, which is classification, or I can do it in another way. I can do it in regression. I can say, okay, just give me the range. Tell me how do you predict that the new number that's going to be the outcome. And that's the same thing that I did. I had to understand if my problem is, do I want to know if the engine is working or not working, which is two categories, or did I want to know exactly like a prediction of time that I didn't priorly predict? So we went with regression. And the second thing we needed to do was feature engineering. Now, feature engineering is probably the most is the part where you actually have to get your hands dirty more than all the other things that you do. And so the two most difficult things in a data science project is, first of all, building your data set in an accurate way, and the second thing is the feature engineering, which takes a long time and is very, very difficult. And so in feature engineering, you find the features that are most predictive. And in our case, it was temperature and maximum vibrations, which is intuitive, but it doesn't have to be intuitive in all cases. And the third thing that we did was optimize the hyperparameters and all the things that are outside of our algorithm. So at this point, we could tell ourselves that we have like a 97% success and we're super awesome and we can go and get this to the field. But we need to still test ourselves. Are we accurate enough? Is this accurate enough? And the first thing that is probably a big problem in predictive maintenance projects is this thing called class balance, which means that we have a class that has significantly more data than the other class. For example, click predictions. Is anyone familiar with that? Say you go on a website and you have a commercial on the website. Who clicks? Nobody clicks it? Perfect. So this is exactly the problem of click predictions. There are a lot of people who don't click the ad and a lot less people who do click the ad. So it's the same problem with engines. We have a lot of information on good and working engines because engines don't break that easily. And we have a lot less data on faulty engines or engines in a certain degradation. So we can't have 100% success if we have a class imbalance. So this is something that's really important to keep in mind and balance your classes. The other thing is precision and recall. It's two mathematical tools that help us understand how accurate we are. So precision actually means how many false alarms we have in our system. The closer it is to 1, the less false alarms we have. And recall means how many times we missed an actual fault. So there's a trade-off between the two. We can't have both precision and recall. And each and every project has to decide what's more important for them. For us, for example, it's recall, because I don't mind having a few more preventive maintenance treatments, only for the not missing out on actual problem at sea. And you have mathematical tools that help you calculate the accuracy. So what we actually did was we processed the data, right? We collected the data, we processed the data, we evaluated ourselves throughout the process. And this is something that can happen, as much as you want. If you don't like the result, you can just add some more data. You can train your model better. You can do some more processing. And then until you get the best result. The most important thing in these projects is to go to the field as soon as you can. Because you will find out that there are a lot of things that you didn't see coming when you're sitting in your lab and you're playing with the numbers. So it's really important, even if you're not accurate enough, to say when enough is enough, and go and test it on real and actual machines. So there are a few important things to keep in mind. It's the data amount. As I said, the class balance is a real issue, and even more important is you have to have a lot of data in order to lower the organizational skepticism. So you have to have a lot of data, and you have to have an accurate set of data, and you have to have it balanced. So that's really important to keep in mind. And if you're planning on going into one of these projects, start collecting data, not now, yesterday. And the other thing that we've spoken about is the engine health. Engines don't break easily, so maybe do things that you wouldn't normally do. Like instead of taking the car to the shop every 20,000 kilometers, take it to the shop every 30,000 kilometers, and then you gain some extra faulty data. So each organization does it in a different way. And the third thing to keep in mind is really the difference between rule-based models and machine learning models. In rule-based models, we have a degradation rate that we're aware of, because mechanical engineers, they know how the life cycle of the machine is supposed to behave. But in machine learning models, we make no assumptions. So that's also something that's really good to keep in mind. You don't make assumptions, and you can find faults that you didn't even think were possible. So at this point, I can tell you that we had a lot of problems, even outside of the technology. Because in a big organization, you have a lot of other problems. And we had a legacy system that we had to put a machine learning engine with a legacy system, and it seemed like impossible. And we didn't have a DevOps team, and we didn't have any machine learning expertise, because my guys are all software engineers. And we didn't have a client that wanted it because of the organizational skepticism that I've spoken about. And so we didn't have a budget. And I could say that it's too many problems and that I don't even want to go into the project. But I decided to look at the solutions instead of the problems. And I decided to attack each one of the problems in a different way. And so, for example, the legacy problem issue, it's something that you can work around. Almost any technological issue that you have, you can work around it. You can find a solution. It maybe cost a little more or be a little more problematic, but you can find a work around it. Same goes for the DevOps team. I didn't have a DevOps team. Okay, so I made them into a DevOps team. So 70% of the time they would write code, and 30% of the time they would have to do DevOps. What could I do? I had no other way. And machine learning expertise, I decided to do a machine learning hackathon, and we took data sets from Kaggle, and I gave them 24 hours to understand how to work with data, and I gave them all experts to sit with them in the teams. And after 24 hours, they knew how to handle data. They knew the basic pandas, and they knew how to even look at data, which is something they didn't have before that. And We pitched to multiple clients because, you know, when you interest one investor, then the other one also wants to go in. And when you interest the right people, you can also get the budgets. So that's what we did. And our project is not the first and not the last project in this field of predictive maintenance. And it's something that's really, really working in the car industry. I'm not sure you all know, but in all the big car companies, they have a predictive maintenance division, and they already collect all the data while you drive. My car is not that smart, but I'm sure your cars are smarter. And they already have data collecting all day long. And markets say that by 2022, this is going to explode and reach an $11 billion annual revenue. It's crazy. It's a really growing market, and I intend on taking over the world with predictive maintenance, and I hope you do the same. And it doesn't have to just be for big ships or big airplanes or anything big, factories or whatever. I have a friend who decided to map all the hard drives in her company. And this is the link for the NASA website if you all want to start playing with it. You can take a photo. And so they mapped out all the hard drives, which means they didn't need a really big machine or a big factory to start with. So you can also do it. And a lot of factories today, they can actually run the other sites that could be even in a different continent. And they can actually see what goes wrong and where exactly in the machine. Like I said, which part of the engine breaks. And in 2016, Siemens, they did a pilot with Deutsche Bahn, the German train company, for all the ICE trains. So if you're taking an ICE train, you should know they're also monitoring that. And it's a really successful pilot. And each and every one of the cloud suppliers nowadays, they also have really, really cool and easy ways to do predictive maintenance. So you can also start there. And if at some point I would just imagine that I would go into the car and it wouldn't break in the middle of driving because I would know exactly what's going on there, I don't have to imagine anymore. It's not something of the future. It's something that's going on right now. And it's something that is really, really cool to go into. And I invite you all to do predictive maintenance with me. Thank you. Questions? OK, thank you.
So you said that you don't, to get better data, you look to not do the maintenance as regularly as you would do normally.
Yes.
How did you manage to sell that to?
OK, so a lot of companies, they make a mistake and they think that when they do machine learning and they come to the client eventually and they say, OK, here, see, it's machine learning, it's really cool, you want it, then they don't want it. So what we did was I met with all the clients prior to giving them the models and the numbers. And I explained it all through the way, and they were with me all through all the steps. So when you take them with you throughout the milestones, they feel that they're connected and they don't feel like they don't know something. And it was an issue. It wasn't easy. Yeah, it took about like 2 years.
Because you need things to break more often.
Yes.
But in your field,
So we didn't take, you're right, and we didn't take engines that were critical. We took engines that were not critical in order to establish trust. So thank you.